usual. Let's start with this one, number 1. Which of the following molecules contains a central atom with Sp2 hybridization? Remember what you need to do to find the hybridization required to give you a symmetrical geometry is you need to know the Lewis dot structure and the number of groups around the central atom. So that includes lone pairs. Okay. So what we're looking for Sp2 hybridization, we need three equivalent hybrid orbitals in order to make that type of structure. And that means it's going to be trigonal planar electronic. Okay. So we look for, let's check out what our examples are. It looks to me like all the lone pairs are written in for us. And you can check out, you can independently determine that these Lewis dot structures are correct. So if we just go down the line, we find there are 4 groups here, there are 4 groups there on any of these central atoms. Those are Sp3s. This one has 3 groups, that's an Sp2. So if you've only got single answers, you don't have any squirrely ones like at the end, like 2 of the above or A and B, that type of thing. Once you find the answer, you can stop. So we found Sp2 right here. That means boron is octet deficient, which is typical for boron. So that's why the answer here is B. It has 3 groups. Sp2 hybridization is required in order to explain its symmetry. In fact, the symmetry here is molecular as well because there are no lone pairs. All right, let's see if I can page. Okay. Which statement about N2 is false? N2. Let's see what we have to choose from. There are several different characterizations of N2 here. Okay, so let's take them one at a time. What about the N2 is a gas at room temperature? Yep, that's true. What about B? The oxidation state is +3 on one end, -3 on the other. Okay. Oxidation state for an element in its most stable form at 1 atmosphere pressure and 25 degrees Celsius is always 0. So the oxidation state for both of the nitrogens equals 0. It's not just the sum of a +3 and a -3 to get you 0. It's each one of them is 0 oxidation state. So B is false. And we can actually stop there. If we went ahead, we know the Lewis dot structure for nitrogen is like that. So that's 1 sigma right here. You can only have 1 sigma. You can have 1 or 2 pi's. That's a pi bond, that's a pi bond. This is a sigma. So C is correct. 1 sigma and 2 pi bonds. How about D? While we're here. Combined with hydrogen to make ammonia. Oh yeah, that's one of my favorite equations. The Haber-Bosch reaction. So D is true. Has 2 pairs of non-bonding electrons. Yep. 1, 2. So they're all true except for that B answer. All right, let's see. I'm going to tackle 3. Yes, let's look at 3. Okay, consider the molecule following hybridization choices. What is the hybridization of the carbon atom that's double bonded in oxygen? There are several of these in sequence. This is a question about that structure. This is a question about the same structure. So I'm going to put the structure up here once, and we'll talk about it. Let's see, middle one. This one. And let's see, chlorine, nitrogen. All right. 1, 2, 3, 4 carbons, a nitrogen, okay, so that one's good. What's the hybridization of this carbon right here? Well, what we need to know is, are there any lone pairs? Carbon is very, very well behaved. Let me just put it that way, as far as the octet goes. So if you find 2, 4, 6, 8, you find an octet around that carbon, you're safe. There are no lone pairs. But you do have 1, 2, 3 groups, which is Sp2 hybridization. So that's why the answer is B. Okay. In fact, let's see. You're going to have a lone pair here, and you're going to have 3 lone pairs for chlorine, in case you're interested. Okay, so that was 3. Let's see, I'm going to have to scroll for 4. 5 is a different molecule, so we'll just write this, do 4. Talk about that same molecule for 4. What's the hybridization of the nitrogen atom? Okay, in this case, you do need to know that you have 1 pair there, because the hybridization depends on 1 group, 2 groups, which means it's sp hybridized. It only needs 2 symmetrical orbitals to work for this bond right here. That's sigma, and this lone pair. That's why you need 2, that sp hybridized, to give you 2 equivalent orbitals. Now, how do we get the pi's? Remember? It's got 2 pi's here. You overlap unused p orbitals. We only used 1 p here. Right? We got 2 extras that haven't been used. Those are the ones that overlap with carbon and give you the 2 pi bonds. Now, that's not part of the question, but I thought I'd make that point while I'm here. But nitrogen in this case is sp hybridized because it needs that lone pair and that sigma bond. Okay, I wonder if there are others. Let me look. Because I've already drawn it once, I won't have to draw it again. I think that's probably it for that structure. The next structure, maybe I can use this one. Well, we'll start over. For 5. Okay, so what do we have? 1, 2, 3, 4, 5 carbons. 1, 2, 3, 4, 5. And let's see. This one is a double bond. This one is a triple with a nitrogen. This one has 1 hydrogen. This one has double bond oxygen. This one has 2 hydrogens. There. This one has 2 hydrogens. Okay, I might remind you that this is an organic molecule. And the convention for writing organics in this this type of structure is that when you write hydrogens next to a carbon, they're only bound to the carbon right here. So that's bound to this carbon. Those two are bound to this carbon. Those two are bound to this carbon. They're not, just because they're in sequence doesn't mean they're bound to that carbon and this carbon both. That can't be because hydrogen can't have two bonds. You only have one bond. So it would be written like, for instance, this one would have the hydrogens out here like that, and then a carbon over here. It would have a hydrogen there to the next carbon. That's the way it would look. Okay. All right, let's see what the question is. Specify the hybridization of each carbon in the following. So those, this is 1, 2, 3, 4, 5 carbons. So really, all we have to do is be sure that the carbons have no lone pairs. It looks like that's 1, 2, 3, 4, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So all the carbons have octets. We have no lone pairs to deal with. So all we have to do is look at the number of bonds, actually the number of groups. So around this one, you have 1, 2, 3 groups around that carbon, which means it's sp2. Here you have 1, 2, 3 around that. That's sp2. 1, 2, 3, sp2. 1, 2, 3, 4, sp3. And 1, 2, sp. So the sequence is sp2s for 3, then sp3, and then sp. So there are 3 sp2s. Throw that one out, throw that one out, throw that one out. So it can only be one of these. sp3s, okay, we're good there. Then sp. So the answer has to be A. Okay? All right, how about, okay, we'll go to 6. Hybridization of selenium hexafluoride. All right, so what do we need to know first? Well, since it's written this way, we need the Lewis dot structure. Selenium's is a chalcogen, so it has 6 valence electrons. Fluorine as a halogen has 7. So 6 times 7 is 42. So we have 48 electrons. Selenium is the central atom. 1, 2, 3, 4, 5, 6 fluorines. Here we go. 2, 4, 6, 8, 10, 12. So we got 36 electrons left over. If we put 6 of them around each fluorine to make the octet, then 6 times 6 is 36. And we use them all up. There are no lone pairs that need to be added to selenium. Okay? So that means around the central atom, we have 1, 2, 3, 4, 5, 6 groups, which means octahedron. Okay? Now we can say what type of hybridization it needs. It needs 6 equivalent hybrid orbitals, right? If we use an S and 3 P's, we don't have any more P's. So we got to go to D's. And we need 1, 2, 3, 4, 2 more D's. D2sp3 is required for here, E, D2sp3. Okay? I used to, when I was studying French in school, I knew I was getting somewhere with it because I started dreaming in the language. If you're not dreaming chemistry, then maybe you're not working enough problems. Well, for some people, it's not just dreaming, it might be nightmares. But at least your brain's trying to make sense of everything. Let's see. Oh, while we're here, let's do 7. Looks like it might have an odd arrangement. Okay. So lead has how many valence? Well, it's in carbon groups, so there's 4. And then 4 times 7 for the halogen is 28, which means 32. So we have lead, 4 chlorines. 1, 2, 3, 4 times 2 is 8, which makes 24 electrons. 6 times 4 is 24. Okay, so we used them all up, just like this. And around the central atom, it's only got 4 groups, so it has to be Sp2 hybridized. Now, as luck would have it, there's no Sp2. So the answer is none of these. All right. The next one, I definitely want to get this one. Okay. Number 8. The name of this compound is Tetracyanoethylene. If you had organic chemistry, you know how to write the compound from the name. But we're going to have to do it the hard way. This is the skeleton structure with no hydrogens. There are no other atoms in here, just those. That's it. Okay? So we know that we can start off with this structure and not have to worry about any extra elements. Okay. So if we're going to complete this Lewis dot structure, we need to know how many electrons we're going to put in. Now, each nitrogen has 5, correct? So 4 times 5 is 20. And then each carbon has 4. So it's 1, 2, 3, 4, 5, 6. That's 24. That means we have 44 electrons that have to be placed. Now, the rule is start from the outside and work your way in. Once you've established all of these, that's 2, 4, 6, 8, 10, 12, 14, 16, 18. So let's see, that's 26 electrons. Okay, so 1, 2, 3, 4, 5, 6. Six times 4 is 24. So we have 2 electrons left over that have to be placed. The rule is you work from the outside in, right? The problem here is that where are you going to put those 2 electrons? You're going to put them here, 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 or here. Right? If we put them on one of these 4, we could form equivalent Lewis dot structures, and then we have to invoke resonance. But if we did put 2, say, just pick this arbitrarily, in order to make an octet, what value would be going this direction with that to make a double bond? No value at all. But you could move 2 pair, 1 pair here, 1 pair here, and make that triple bond. Right? That still takes care of this nitrogen and that carbon, but we don't want that lone pair there if we're going to do it that way. Now, if you do that all the way around, the only logical place for that lone pair is on one of these 2 carbons there. Okay. So if we do that all the way around, like that, then we only have to say, all right, there's only 1, 2, well, actually, this one has an octet, 1, 2, 3, 4, but this one doesn't. So if we move that pair over here, now we have an octet for everybody. Okay. That was the trick for this one, is knowing where to put that the last two electrons. On any of these, it just wouldn't work. You'd never get an octet. If you put it on one of these, then you're good to go. All right, so what's the question? How many of the atoms are sp hybridized? Sp hybridized means two groups, correct? Okay. And remember, when we say hybridization, we are also talking about electronic. So this atom has 1, 2, it's sp. This one has 1, 2, it's sp. So you have 2 sps here, 2 there, 2 there, 2 there. 2 times 4 is 8. You have 8 atoms that are sp hybridized. That's why the answer is D. Okay. Now I'm going to leave that structure there because there's another one further down the line using the exact same structure. I think it's in the 20s. Yeah, 23. And I don't want to have to draw the thing again. So let me scroll down to 23 and we'll knock that one out using this same structure. There we go. Okay. Using that same structure and with this Lewis dot structure that we've already drawn, now how many sigma and pi bonds are in the molecule? So many sigmas, so many pi's. Remember, you can only have one sigma between two atoms because it's on axis. So just count up the number of bonds. Actually, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 sigmas. How many pi's? Well, we've got a triple bond here, so that means there are 2 pi's. 2 there. 2, 4, 6, 8. 9. There are 9 pi's also. Okay. That's why the answer is D. And that's the only other question with this structure. Okay, now I can go back and pick up where I left off. Number 9. Back up. Actually, I've already answered this one. A pi bond is the result of, now this is with the valence bond theory, right? The pi bond results from the overlap of 2 p orbitals, unused p orbitals, right? But you've got some squirrels in here that are giving you wrong information. This one can't be it. You can't overlap s orbitals and get a pi bond. Can't overlap an s orbital with anything. Okay, so C, D, or E is where we're at. Overlap 2 p orbitals along their axis. That can't happen because you can't have the pi bonds unless you've got at least 1 sigma bond. So the overlap has to be sideways, off axis. Sideways overlap of 2 parallel p orbitals. That's the one right there. I said that E was possible, no, because it's s orbitals. So D is the answer because it's the only one that fits the theory. Okay, let's see. Let's take a look at 10 also. So here are our molecular structures. And let me just put them up. If this one has double, 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 this one has double there, this one has double there. And these are the formulas for each one. But we want to focus on this because I would have to say first that this is another one of those organic conventions. We write organic molecules. When we write them like this, we don't write the carbons in. It just gets too messy. So whenever two lines come together, if there's no atom written there, then it's assumed to be a carbon. Now, if we put something else in there, like say we stuck a nitrogen in here, some molecules like purity, we stuck a nitrogen in there, then yeah. But if there's no atom there, it's a carbon. Okay, and carbons form 4 bonds each, somewhere or other. If it's at all possible, they form 4 bonds. So if you've got 1, 2, 3 bonds here, that means the 4th one is understood to be a hydrogen. So that means hydrogens all around here. Okay. That's why the formula is C6H6, right? 6 carbons, 6 hydrogens. Okay. For this one, you got 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. These have 2 hydrogens each. That's why the formula for this one is C6H8. And then for this one, there's only 1 there and 1 there, but there are 2 here, 2 hydrogens there, 2 hydrogens there, 2 hydrogens there. Okay, that's the convention. All right, now what's the question? Which molecules have p orbitals that share an electron pair to create a pi bond? Which molecules have p orbitals that share an electron pair to create pi? Which ones have pi bonds in it? That one does, that one does, and that one does. They all 3 have pi bonds. That's what that means right there. If they're sharing electrons to form a pi bond, all the above. They all have pi bonds in them. They have different numbers of pi bonds, but that wasn't the question. The question was, do they have pi bonds? Yeah, they all 3 have pi bonds. Okay, 11 uses the same set of structures. So we're just going into 11. Scroll. Okay. The next question is, which molecules have equivalent carbon-carbon bonds throughout the molecule? All right, let me remove some of this mess. Now that we know that there are hydrogens out there, we don't have to write it. Clean this thing up some. Okay, what do we know about single, double, and triple bonds as far as energy and bond length goes? Single bonds are the lowest energy and the farthest apart. Then double bonds get the nuclei closer together and they're stronger bonds. Triple bonds, stronger yet, and get closer together. But we don't have any triples to deal with here. We're just comparing singles and doubles. So when they're saying CC bonds, that might be misleading. It's not necessarily a CC only. Right, with a single bond, it could be a C double bond. Just when it's abbreviation. Equivalent carbon-carbon bonds throughout the molecule. Okay? These are not equivalent. That's a single, 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 and a double. So that one is a shorter bond. This one has 2 shorter bonds and these single bonds. Well, actually, well, I don't want to muddy the waters, but what you'll get is those 3 bonds are equal in length. And by extension, all 3 of these bonds are equal. I mean, all 6 of those bonds are equal in length. We know that. This is benzene. And it just so happens that the way we write it here is we're forced to write it that way because of the valence bond theory. We have no choice. We can't write it any other way. So it resonates with another one that looks like this. Okay, so they resonate back and forth between those two. We have to write it that way. If we, at the end of the last chapter, the last lecture, we talked about delocalization. That's what happens here. So we use sort of what we knew about the molecular orbital theory to reconcile this problem. So all these bonds are equal in length. And sometimes for that reason, benzene is written this way. Okay, that means that all these bonds are the same length. Okay, so that makes the answer 1. That's the only one with equivalent bond lengths. Now these bond lengths are the same, but for, well, it's due to delocalization of electron density around over those 3 bonds, but these are left out. You would see something like that with your, remember the nitrate molecule? Like with a negative charge. And we delocalize the electron density over all of those 3 rather than write resonant structures. So it's a similar idea, this one to that one, then by extension, this one. But it all has to do with delocalizing the electron density. That tends to lower the energy and stabilize the molecule. If that were not true, then it wouldn't happen. All right, 11, let's see, I want to do 12. I want to do 12 because it introduces the shorthand version of writing molecular orbitals. So remember when we wrote, when we had the energy diagram, increasing energy, and then we had let's see, we left out the 1s's. So if we were in the second period here, and we were doing diatomic say with one of these, then we would write just the 2s and 2p derivations for molecular orbitals, and they would stack up like we have a sigma from a 2s, then we have a sigma star from a 2s, then we would have let's see, excuse me, sigma from a 2p, and then we would have pi from a 2p, and then we would have a star from a 2p, and then we would have a sigma star. So that's the way they would stack up if there were no sigma pi mixing, sp mixing. That's the way they would stack up. You would have the sigmas like this, the pi's in the middle like that. If there were mixing, then this one would be underneath, this would be up here. But in this case, there's no mixing because it goes sigma pi pi. Well, it doesn't show the sigma, but it's because we don't need it. But the point here is that this is a shorthand way of writing it. You just take this, the lower energy, it's like writing electron configurations for an atom. The left-hand side is the lowest energy. So if you just take this whole thing and lay it flat, that's what it would look like right there. And you know that all the sigmas always have a maximum of 2 electrons each. And the pi's have a maximum of 4 because you have 2 and 2. Until we get to this one, this sigma star, we only have 2. So they have to go in like that, correct? Thumbs rule. So all these would be filled underneath there. And then it shows that as the superscript there, 2s and 4s. Okay, so what's the question? What's the bond order for this species? Well, you don't need it written like this. You can tell which one is bonding and which one's not bonding, right? From the asterisk. So the bond order here would be, let's see, well, translating that here, we would have 2, 4, 6, 8. 8 bonding minus anti-bonding, 2, 4. Correct? That's 2 bond order. Okay? So the only reason I want to stop on this one is because it's unfamiliar notation. But it's logically based. It's drawn from that structure. It's just quicker to write. And it gives you all the information you need. You just have to recognize, if we had a question here about paramagnetism or diamagnetism, then you could also tell from this one, if you remember that pi's can have 4 electrons total. And the reason they can have 4 is because they're 2 degenerate orbits here. And if you only have 2 electrons go in there, they're unpaired, which means it's paramagnetic. If you have another electron in there, it's still paramagnetic. But if we have another electron, now they're all paired, it's diamagnetic. Okay. It also changes the bond order. All right, that's 12. Let's see. Well, while we're here, 13. I know I'm going to run out of time, so I'm not worry about it. As the bond order of the bond increases, the bond energy does what? Bond order roughly parallels single, double, triple. So as the bond order increases, the bond energy increases. It becomes stronger. It takes more. You have to put more energy in to break the bond. So the bond energy increases, so it could either be A or C. And the bond length decreases. Anytime you increase the bond energy, you draw the nuclei closer together. So increase and decrease, and it would be this one, C. Okay. Let's see if we can do this. If we have this molecular orbital configuration, sigma, 2s with 2, sigma star, 2s with 2, and pi. Okay, this one splits out. We would have written this pi 2p and put these 2 electrons on that. But this one splits them out. So these 2 orbitals are degenerate. They're equivalent in energy. And I'll just write it the way they have it. 2py and pi 2p. See? Oh, it says X. Be consistent. Okay, there's 1 electron each. So that means these electrons are unpaired. Okay. All right, now let's see, what's the question? This is the orbital description for the ground state of which one of these? All right. First thing you'll notice is these are homonuclear diatomic. They're made from the same elements. There are 2 of them together. So we split it in half. Right, we have 2, 4, 6. 6 electrons. That means we have 3 electrons from each one. Or I suppose we could have had 4 from one and 2 from the other. It doesn't matter. We have 6 electrons total. Okay, how many of these have 6 electrons? Well, lithium, and we're talking about valence here only. Right? We're already up 2. So valence would be, let's see, lithium has 6 electrons in its ground state, where this one, no charge. That would suit that one, but that's not here. Okay. So how about beryllium? Well, beryllium has 1, 2. Oh, excuse me. No, I'm sorry. I don't know what I was thinking. This only has 2 electrons. And 2 plus means it only has 1 electron in its ground state valence. All right, so that one can't be it. How about beryllium? Well, beryllium has 3 each, so it has 6 electrons. Yep, that could be it. Could be it. Should be it. Oh. You guys need to say something. Because I confused myself. I know I'm confusing you. Beryllium only has 2 electrons each. Right, so it has 4. Boron. That's what I was looking at. Boron has 3 each. It has 6. There you go. There's your answer. Sp2 boron has this configuration. Okay. That's what I get for trying to hurry through. All right. Yeah, let's take a look at 15. And then we'll start skipping a few. How many unpaired electrons in the F2 2 plus ion? F2 2 plus ion. We're looking for unpaired electrons, and it gives you the orbital structure right here. Right? It doesn't tell you where the electrons go. It just tells you that's the order of molecular orbitals for this species. So we need to know how many electrons we have to place. Well, notice that they're only giving you the second period values. These are the valence electrons orbitals. Right. So we would only add up the valences here, which would be 7 each. Times 2 is 14. Minus 2 to make that 2 plus charge. So we only have 12 electrons to place. Okay, so sigma 2 S, sigma 2 S star. Let's see, there should be no mixing. Right, that's good. Sigma pi sigma. This is going to be 2p, 2p, 2p. This one's going to be a star and a star. Okay, now we can place our 12 electrons. We start use alpha principle, lowest energy to high energy. So that's 2, 4, 6, 4 is 6 and 4 is 10, right? So we need 2 more. This one has nothing. Okay, now what's the question? How many unpaired electrons? Unpaired electrons. Those are paired, because you can only have 2 each. You can have 4 in this one, they're all paired. You have 2 degenerate orbitals like this, like this, like this, like this. This one has 1 here and 1 here. So how many unpaired electrons? How many electrons? 2 unpaired electrons. That's why the answer is C. All right, let's see. We got some repetition here. Skip down to, how about 22? See if I can page down to that. There it is. 22. What's the hybridization of chlorine in ClF2 with a single positive charge? Okay. They're halogens, right? Halogen, halogen, halogen. 3 times 7 is 21. Minus 1 to make the positive charge. 20. Right, so we're going to have a chlorine, a fluorine on either side. So that's 2, 4. 16 left over. So 6, 12 more on the fluorines gives us 4 left over, right? So there we've used them all up. So what's the hybridization on chlorines? 1, 2, 3, 4. Sp3. Okay. We already did this one. 23. Let's see. One of this 24. Okay, work. Is there anything to be gained from that? Complete the Lewis structure. This molecule has how many sigmas and how many pi's? Okay, we'll do that one. 24. So this is CH3, CH, CH3, C. Yeah. If those are all the atoms that are present, then we know that this one has 3, 4. This one's okay, just like it is. That one's okay, like it is. This one has 1, 2, 3, 4. That one's okay. It's got an octet. 2, 4, 6, 8. This one doesn't. So what we typically do is if we have an oxygen there and we know there are no other atoms, then we make the oxygen double bond. And then that means that oxygen has to have 2 lone pairs. It's like water. Water is the same way. Right? It has those 2 bonds like these with hydrogens, and we know it has those 2 lone pairs. Okay, so in this one, how are we going to do this one? Well, normally what would happen is to make an octet here, we would have that. Then we would take 2 of those pairs and make a triple bond. Now you can check me out. You can go back and add up all the electrons, right? And then work your way in with the unused electrons. You should end up with exactly the same answer. But once you know this, how many sigmas and how many pi's? Well, there are 3 sigmas here. Remember the notation. There are 3 here, 1 there, so that's 4. There's 1 there and 1 there, so that's 2. But there are 3 here. Single bonds are sigmas. All right, we've already covered, let's see, 4, 5, 6, 7, 3 there. And we have 1 here. We have 1 here. We have 1 there. So that's 1, 2, 3, 6, 9, 13 sigmas. So it's either this one or this one. We need to find out how many pi's there are. Just look for the doubles and triples. So there's a pi, and there's 2 pi's. So we have 3 pi's. Okay. I kind of rushed through that, but if you draw the Lewis dot structure the old-fashioned way, you should end up with exactly this one. And there are no tricks. You work from your outside in, and everything should be fine. All right. Now I got 26 marked. Scroll and get to it. 26 and 27, maybe. Here's another one where we have, this is the skeleton, which means there are no other atoms. Okay. So 2 times 5 is 10, plus 8 is 15. 2, 4, 6, 12. Okay. 2, 6, that's 12. Okay. So now you have to make your octets. Well, the only way you can make an octet is to move these into hydrons. So we do that, 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 that. Now we've got our structure. Then we can answer the question. How many pi bonds does the molecule contain? 1, 2, 3, 4. 4 pi's. Okay? Let's see, all of this with 27. Okay, 27. Drive this point home. So we've got A, B, C, D, and E. E says B and D. Okay. A is C2H2, C2H4, C2H6, and C2Cl4. Okay, we draw the structures here. We find that we're going to have carbon, carbon, and then 2 hydrogens, right? We'll come back and complete it in a minute. So the carbons are bound together like that for each one of these. And then this one has a chlorine here and chlorine here. This one has 3 hydrogens. This one has 2 hydrogens. And that's what we're writing here. Then we draw our structure, right? So this is 2, 4, and 8 is 12 electrons. This one is, 8. 8 plus 2, wait, no, that's not right. 1, 2, 8, 9, 10. 10 electrons. 4 and 4, 1 and 1. 8 plus 2 is 10. And this one is 8 plus 4. Right? 1, 2, 3, 4. 8 plus 4 is 12. And then 8 plus 6 is 14. This one is 8 plus 7 is 14, 22. 7 and 7 is 14. 14 plus 8. Yeah, 22. Okay, so we've got 2, 4, 6. There's 4 left over. Can't put them on the hydrogens. So we can do like this, like that maybe. And we've got 12 minus 2, 4, 6, 8, 10 equals 2 electrons. So now to go there. Now we have 2, 4, 6, 8, 10, 12, 14. Those are all used up. And here we have 2, 4, 6 equals 18. 16. So that's 12. It's 4 electrons, so we can do 2 here, 2 here. Now we need to make octets. 2, 4, 6, 8. There's your octet. This one goes over here. 2, 4, 6, 8, 2, 4, 6, 8. 2, 4, 6, 8, 2, 4, 6, 8. This one what value would there be in making a double bond with chlorine? It would satisfy 1, 2, 3, 4. An octet here, an octet there. But then you would have, well, let's just cut to the chase. Hold on a second. I don't think I calculated that right. 7 and 7 is 14. 8 is 22. That's right. 2, 4, 6. Yep, minus 6 should be 16. Okay. Minus 12 is 4. So we get 4 electrons. Yeah, okay, that's right. That's right. Okay, so to make a long story short, the best way, actually, we could prove this, that we'd rather move this pair here and that pair there and make a triple, rather than moving a pair from here and making a double there. All we have to do is calculate the formal charge. Yeah.
I just noticed this. I think you're missing two formulas on the fourth one B. So C2Cl4.
Thank you. That's why it didn't work. Yeah, that told us not how to do it. Okay. Now it makes sense. Okay, so we have count it up again. 8 for carbons. We have 1, 2, 3, 4 times 7 is 28. Means 36. So 2, 4, 6, 8, 10, 26. So 6 more times 4 is 24. 2. Okay. There we go. So now we just need to move these two over here and make a double bond. Okay. Oh, back to my point. Making a double bond here, 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 or here would give us, all we have to do is just calculate the formal charge. You would find that the formal charges are best like this than they are with doubles here or any of those others. Okay. This is the preferred Lewis-Dot structure because of the formal charge calculations. Okay, now we have to answer the question, which contains the shortest carbon-carbon bond? Okay. Well, we know that this is going to be the longest carbon bond because it's a single bond. This one will be shorter, that one will be shorter than this one. This one will be the shortest because it's a triple bond. Now, if we didn't have that one, what would we have to do? We'd have to tie break with this one or that. If you're ever presented with that problem, which is not the answer here, but if you ever have to break the tie, look at electronegativities. The electronegativity of chlorine is much greater than hydrogen. So it's going to draw electron density away from that bond and weaken it. So that would make this bond stronger than that one. In fact, organic chemists use that concept day in and day out to facilitate certain types of reactions. They attach, particularly for what's called the Grignard reaction. They use chlorines to shift the electron density in a position where it would promote a certain type of reaction. All right. Let's see. I'm already out of time. Well, as usual, I'm gonna keep talking. If you have to go, then that's fine. I'll post it by this evening, the video. Let's see, do I want to do 28? Nah, let's do 29. Here we go. Which of the following species is paramagnetic? In order to be paramagnetic, we need unpaired electrons, correct? This one, and this will be available in, yes, thank you. All you need to do is look at the useful information. Right? It's got your structures right here, except for this one, the dilithium. Oh, but it does have, the one above it does have the order of orbitals. Right? So then all you'd have to do is just fill in the electrons. Well, actually, lithium only has 2 electrons. So you just take, there we go. 3, 2, S2. All right. That's diamagnetic. Those are paired. This one's diamagnetic. I'm doing them out of order, right? That's deep. Then the others are right here in your A, B, C. This one, and this one. So if you look at carbon, carbon's got all paired. That's diamagnetic. Oxygen, unpaired. That's para. And fluorine is all paired, so it's that. So oxygen, B, is the only one that's paramagnetic out of this group. Okay. Let's see. Go back. 30. Now let's do 30. For how many of the following does the bond order decrease if you add 1 electron to the neutral molecule? Okay, so we've got boron, carbon, phosphorus, and difluorine. Phosphorus is not in this group, but phosphorus is in the nitrogens, so it's going to behave like nitrogen. So it's kind of like this one. Only instead of the second period, it's the third period. So if you look at nitrogen, you find out that nitrogen has, if we just substitute in 3s, it's sigma star 3s, and then pi 2p, 3p, and then sigma. Then we find that the same number of valence electrons are here for that one. 2, 4, 10, 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. There we go. They're all paired. Okay, carbon is sigma 2s, sigma star 2s. Oops. Yeah. I2p. So there are 4 each, 8, 2, 4, 8. Boron is sigma 2s, star 2s, and pi 2p. We have mixing here. That's why it's that order. And boron has 6 electrons, 2, 4, 6. And fluorine. Okay, so fluorine is going to be Okay, we'll see it. 2s and sigma p I2p. Let's see, how many do we need for? We need pi star. There we go. Fluorine has 14. 2, 4, 6, 10. Okay, the key to this one is, now that we have the structures, we know where all the electrons go. We don't actually have to calculate the bond order. And the reason we don't have to calculate the bond order to answer this question is, it just says which will decrease the bond order if you add an electron. Remember, the bond order is bonding minus anti-bonding divided by 2. So if you add an electron to an anti-bonding, it's going to decrease that value by 1/2. Whereas if you add one to the bonding, it's going to increase the bond order by 1/2. So knowing that, if we just add an electron to this one, will it take an electron? Yeah, it's only got 2. So this one's going to increase the bond order. If we add 2 here, oh, carbon. What comes out here from carbon? Sigma 2p. Because this one's full, we got to go to the next level. Yeah. So if we add one to this one, it's going to increase the bond order. If we add one to this one, or what comes next? Right. Pi, sigma, pi star. If we add one to this one, it's going to decrease the bond order. Oops, that's a 3. If we add one to this one, let's see. Fluorine, no mixing. And this one. Right? If we add one to that one, it's going to decrease the bond order. So actually, out of all these, 2 of them will decrease the bond order if we add an electron. These 2, P2 and F2. And the other 2, we increase the bond order. I wrote 3 up there. That should have written 30. Okay, let's see. Yeah, I got 31 marked. I need to scroll down. Which one of the following has the largest bond order? These are all dinitrogens with various things being done to them. The best way to work this one is start with your neutral group and write its configuration. Let's see, nitrogen, and it's going to have sp mixing. Okay, so we're going to have 2s star, 2s, we'll have sigma p, pi, mixing. Yeah, oh, mixing. Pi 2p, sigma, pi star, 2p, sigma, star, 2p. There you go. Okay, so we have 5 valence electrons rolling in the valence shells here. 10 total. So that's 2, 4, 8, 10. That's it, right? Did I do that right? Second guess myself. 2, 4, 6, 8, 10. Yeah, yeah. I think I'll only need this one because one of the ions adds electrons. Okay, so if this is A, what's the bond order? 6, 7, 8 minus 2 is 6 divided by 2 is 3. Bond order is 3. Got a triple bond. How about B? N2 minus means we add an electron. If we add an electron here, that decreases the bond order by half. C. Now we're going to add 2 electrons. If we add 2 electrons, we go down another half to 2. D. We're going to subtract an electron. So it's a plus charge. So now we're going to have this is plus, minus an electron. So we have to take that electron from a bonding orbital, which means we're decreasing by half. And then E. Now we're going to subtract 2 electrons. We decrease it by another half. Okay? So the largest bond order of this series is the neutral dinitrogen molecule. Okay. Let's see here. There's a lot of repetition. 44 uses that same. The highest bond order for that, we go down to 44 based upon the same. There it is. The strongest bond is going to be the highest bond order. So that's nitrogen again. Then there's one other one. Yeah, the next one, 45. Which of the following has the highest bond association energy? It's another way of saying the same thing. Dinitrogen. Okay. 49 through 55 are fill in the blank, and they're basically just definitions. Okay, so I think you guys can probably deal with those. Most of my students do okay with memorization, so we have to think we have problems. For each of the following that are, check the box for each of the following, 56. Check the box for each of the following that are paramagnetic. That is, which ones have lone pairs? Right. That's why I gave you that useful information with, let me write them up here first. A through I. Okay. This one is O2. We know O2 is paramagnetic. We've already done that. Because it has unpaired electrons. O2 minus. Where are those unpaired electrons for oxygen? The unpaired electrons for oxygen are I2P star. There are 2 of them. So if we add another one, what's that going to do? It just changes that to 3, right? But you still got 1 unpaired. So that ion is also paramagnetic. But if we add another one and make 4, now they're all paired. And that ion is diamagnetic. Diboron. Here it is. Diboron has pi2p with 2 electrons in it, so it's paramagnetic. And I'm just looking at this chart right here. So that one's paramagnetic. Boron, carbon, dicarbon, they're all paired, so they're diamagnetic. F, dinitrogen, we know that one's all paired. Done that one ad nauseum. F2, those are all paired also, diamagnetic. And Cn minus, that might give us some trouble. So we need to look at how are they ordered. Carbon and nitrogen both come from the side that experiences SP mixing. So that's an easy call. You just use the SP mixing format and we get, I'm going to do the whole thing for this one. 2s sigma star, 2s sigma 2p, oops, sorry, mixing. Pi 2p, sigma 2p. Then pi star, sigma star. We may not need all those. So how many we have in the second, in the valence shell is 4 for carbon, 5 more for nitrogen, and 1 more makes 10. So we have 2, 4, 4 is 8, there's 10. Okay, that's the structure. This one is paramagnetic. Excuse me. Diamagnetic, they're all paired. And then the last one, P2. P2 is the same as nitrogen. Because it's in the same family, same valence, molecular orbital structure. Mixing theories, valence and valence bond. We're only dealing with molecular orbitals derived from valence. But it's the same as nitrogen, it's diamagnetic. So in the interest of time use economy, we do it that quick to answer the question in a test and move on. Let's see, which ones? A, B, and D. A, B, and D are paramagnetic. Okay. Let's see. I think we're up to the point now. Give a bond order for each of the following. Okay. 57. Oh, I need to scroll back. There we go. 57. So we got H2 plus, H2 minus. We did this one in class. We just did this one. Cn minus Cn, Cn plus. Okay. So this one is easy. We've got a sigma from the 1s, sigma from the 1s, sigma from the 1s. This one has 2 electrons in it. This one only has 1. This one has, oh, we need to go up. Sigma star. So this one has 3, 2 there and 1 there. This one is, let's say, sigma 2s, sigma star 2s, pi 2p, sigma 2p, pi star 2p, and I'll go ahead and write that. Okay. So this one is what? 4 and 1 is 5, 10. 2, 4, 8, 10. Okay, these. Okay, so if we're going to take away an electron, it's going to come from that. So now we're only going to have one there. And this one, we take away another one. So that one goes away completely. And that's all we have right here. Okay, bond order. Calculate the bond order. All right, bond order for this one is 2 minus 0 divided by 2 is 1. We're decreasing a bonding, so it's a half. We're increasing in an anti-bonding, it's also 1/2. This one is 2, 6, 7, 8 minus 2 is 6 divided by 2 is 3. Take away an electron comes from this one, a bonding orbital. So it's 2.5. Take away 2 more from the bonding order, it's only 2. So there you go, 1, half, half, 3, 2.5, and 2. Now that's the quick way to do it. If you feel more comfortable with going through the whole thing, do the calculation, that's fine. Right? There's really no time limit on the exam, so you can take all the time you need. Let's see. Too far. Consider the structure of glycine. Let's see, you had biology or anatomy and physiology, you know what glycine is. The simplest amino acid. The amino acids are the subunits, structural subunits of proteins. Okay, so indicate the hybridization of each nitrogen and carbon. Right, so let's draw it. In fact, let's draw it out completely. That, this, there like that. Then the second carbon, here, here. Then nitrogen, H. It has to have a lone pair. Okay, this one has 2 lone pairs. And these are going to be important for doing the hybridization. You got to know where your lone pairs are. So that's an octet, that's an octet. That's an octet, 2, 4, 6, 8, that's an octet. Okay, now we can say something. Hybridization of each nitrogen and carbon. So the oxygens are left out. This one's 1, 2, 3, sp2. This one's sp3, and this one is sp3. So sp2, sp3, sp3. And then what are the total number of bonds in the molecule? The total number of bonds is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 bonds. How many pi bonds? Only one. 1 pi. Okay. All right. Oh. Explain the concept of delocalization. This one might have been, I think this one was in the version 1 also. There's some overlap here. The concept of delocalization in the SO3 molecule indicate how this relates to resonance. So if we draw SO3, that, like that, like that, then we have 1, 2, 3, 4, all in the same family. So it's 4 times 6, it's 24 electrons. 2, 4, 6, which makes 18 electrons, right? 6 times 3 is 18. So we're good there. Okay, now to make an octet, we can draw a lone pair from any one of these oxygens. Right? If we do it from this one, it gives us that structure. If we do it from this one, it gives us that structure. And if we do it from the last one, it gives us that structure. Now, with the valence bond theory, we have to resonate. Like that. We can draw these Lewis dot structures, and in order to make an octet, we can make an octet with any one of these oxygens to make the octet with sulfur. And each one is equivalent, which means we have to resonate. So the concept of delocalization says that we know that all of these bonds are equivalent in length and strength. Right? So delocalization says that this is not really a double bond. In other words, it's spread over the entire molecule. The lone pair that we indicate as a double bond is actually delocalized over the molecule. And these three resonating structures are best represented by one structure that shows the delocalization over the entire thing. This is an example, again, of sort of combining concepts from valence bond theory and from molecular orbital theory. And like I said before, nature just does what it does, and we have to explain it. Nature says, and experimental evidence says, all of these bonds are exactly the same length. Right? So this is not really the best representation. Delocalization answers the question the best. All right, let's see. Let me come down. There, two more. You good to go? Okay. Oops, I need to scroll a little bit. Right, this one is still in the table, so it's kind of like a detective story. You have the information up here that you need to use to fill in these values. Right. So we have these three molecules, A, B, and C. Right. We're going to look at the electronic geometry. We're going to look at hybridization. We're going to look at bond angles and examples. Okay, so that. Now the problem is given to us in these forms. Molecule A has hybridization of sp3. That's given to us. There. Molecule B has two more effective pairs, electron pairs around the central atom than molecule A. Okay, we have to make an assumption here. Well, actually, we don't have to make an assumption because electronic geometry says sp3 is tetrahedral. It's tetrahedral for electronic geometry, and if all of those groups are occupied by an atom bound to the central atom, then the bond angle is going to be 109.5. And a good example is methane. Okay, so how about molecule B? Molecule B has two more effective pairs around the central atom. Okay, if we got two more pairs, the only way to do that is with D's, which means the electronic structure is octahedral. If we look at a representation of the geometry of an octahedron, it's got a square in the middle and then two apexes. The bond angles could be 180, or they could be 90 degrees, or it could be 90 degrees over here. Everywhere else is 90 degrees. So the bond angles here are possible 180 and 90. And my example for that is sulfur hexafluoride. In this case, we had no lone pairs, SF6. Used all of them up. There could be other examples here, especially for an electronic geometry where you have one lone pair or two lone pairs, whatever the case may be. Let's see. C consists of one sigma and two pi bonds. Okay, the key here is when can you have pi bonds? Only when you have sigmas. So if you've only got one sigma, then the other two pi's have to go here. They can't go anywhere else because we don't have any more sigmas. So this molecule has to be linear. And the hybridization must be Sp. And no other option. The bond angle, of course, is going to be 180 degrees. And a good example. Now this says molecule A consists of, that's misleading. Actually, no, it doesn't have to be. It would be misleading if we tried to shoehorn in here acetylene, because it would have 3 sigma bonds. So this one is the best example, or one good example, is the carbon monoxide. Right. There are no bonds out here. So now we only have 1 sigma, 2 pi. That's okay, that's good. Dinitrogen would work well there also. Okay, I think I have one more, and then when we're done with this review. Oops. This one is not as hard as it looks. Draw a molecular orbital diagram for dioxygen and dinitrogen. You got it right there in the review document. He just copied it. One's going to have sp mixing and the other one's not. So oxygen won't have and nitrogen will have sp mixing. And then, of course, they'll have different numbers of electrons. But once you finish drawing those, the purpose of having drawn those is to explain why the removal of one electron in oxygen strengthens bonding, while the removal of one electron in dinitrogen weakens bonding. It all depends on where those electrons come from. For oxygen, we're taking an electron from anti-bonding orbital, but for nitrogen, we're taking it from the bonding orbital that weakens the bond. Whereas with oxygen, it strengthens the bond. And that's what all this mess down here says. Okay.